I'll just speak louder. Okay, perfect. Good morning. My voice is my passport. Verify me. Those lines came from arguably one of the best hacking videos ever released, called Sneakers in 1992. Anybody who thinks that the Disney film Hackers was the best needs to leave right now. What was cool about that movie is that it assembled a crew of amazing hackers and cryptographers and freakers and general miscreants to try and stop a really ugly power from doing something really, really bad. And this is what we tried to do for this project. Now, in the Sneakers movie, the plot was quite simple. There was a mad mathematician called Dr. Janet Gunter, and he built a box, this box, right? And this box had the capability of destroying the world's encryption. Now, in 1992, that might have been seen as somewhat far-fetched, but actually, fast forward 31 years, and the reality is that future is pretty much coming to where we are right now. Now, a little disclaimer. Throughout this talk, you are going to hear the term crypto. We are not referring to the Ponzi scheme of Web3 and NFT monkeys. We are talking about cryptography. So please do not associate us with that. But as with all things cryptography, we as an industry stand on some serious shoulders. Now, out of interest in the room, how many of you here have ever thought about post-quantum cryptography or quantum computing? How many of you actually care? Okay, so that's actually not bad. The thing is, a big chunk of how the internet was built was around cryptography, and we stand on mega shoulders. For example, this gentleman, Taher El-Gamal. He was responsible for the birth of Secure Sockets Layer, OpenSSL. And this was important because when he joined Netscape, they had the browser and they needed a way to make sure that people could do stuff on the early internet and the World Wide Web that wasn't insecure. So he and his team came up with the idea of SSL, and they started to build it. Now, incidentally, SSL 1.0 was never released to the public because it was insecure. But that's fine, because SSL 2 came out. Unfortunately, SSL 2 also had security vulnerabilities, so they had to remove that. And then finally, in 1995, SSL 3.0 came out. Now, that showed the complexity of how to do cryptography on the internet. What was born about that was a project called SSL EAY. And this was the first implementation of the SSL protocol by Eric and Tim Hudson. And this was really important because SSL EAY allowed people to start taking Taher's original idea that encryption and cryptography should be for everybody. It shouldn't be for the 1%. It should be part of what you can do when you build stuff on the internet. Now, Eric and Tim joined RSA, and out of that was born a project that all of us use to this date, OpenSSL. The first version of OpenSSL came about in 23rd of December 1998. And this is really important because up until then, we didn't really know what was inside that box. Now, the plot for Sneakers, if you've never watched the film, is fascinating because the idea is you had this prop that could break encryption, like I said. Marty and his team were put together to steal it from this mad mathematician by the NSA, or at least he thought it was the NSA. And when they got access to this box, they wanted to understand how it worked because they didn't really know. And for me, that sums up the modern problem with cryptography. Cryptography has always been the dark arts. As my colleague Mark has always said, wizards came to the village wearing robes and Birkenstocks. We're talking mathematicians and cryptographers. And they handed over a potion, a magic potion that protected you from the evils of the world. And you as a villager, a peasant, said, well, what's in the potion? And you were told, shut up, peasant. I'm a mathematician. You don't know what you're talking about. Today, that is still cryptography. We use cryptography. We think we know cryptography. But the reality is we don't know anything about how it's built or where it's used. And this matters because significant changes are happening with how computers start to break cryptography, most predominantly post-quantum cryptography and quantum computing. So what we've decided to do was Mark and I, 18 months ago, had a what-if moment. We were like, what if we could build a series of engineering blocks that could make use of probably one of the best static analysis tools that we've used, CodeQL, but then do it at scale and look at how the world's supply chain is either vulnerable or not vulnerable to the threat of quantum computing and quantum cryptography. And I went to GitHub and I went to Microsoft and said, here's my crazy idea, can you help us out? And they said yes. And what we set about doing was building these blocks that say, we want to look at all the world's supply chain. We want to look at every single dependency that people use when they build code, be it in C++, Java, Golang, Python, maybe Ruby. We're not doing PHP. I'm sorry, we draw the line there. We thought, let's understand how cryptography is used. Let's understand how key exchange happens. Let's understand the algorithms. So we thought, well, why? Simply put, RFC 1320. Anybody here aware of RFC 1320? One person, two people, you utter nerds. RFC 1320 was the introduction of MD4 in the early 90s. This was really important, a great hashing function. Unfortunately, like most things, there was a collision-based attack and it was deemed insecure. Thankfully, the elders back then decided a way of making the world know that some parts of cryptography were not bad, and that was RFC 6150. It said, don't use it anymore. It's historic. Granddad needs to go to bed now. The problem is, up until then, we've never really moved into a phase where we know bad cryptography, but we keep on using it. So for example, SHA-1, MD5, all these really, really insecure things that have been broken, we continue to use. So we set about saying, all right, we have source code, we have lots of it. What's the easiest way to look for MD5? Naturally, most people will go grep, right? Let's grep for the code. And indeed, some cases that does work, but it doesn't work at scale. And that's what we set about to do with CodeQL. We decided we're going to do this at such a massive scale, we want to start building up a massive database of every single bit of code out there, the cryptography it uses, and how it interacts with others. And why? Well, up until now, cryptography has always been either something that we're scared of, the wizards and the Birkenstocks, or, as my ex-pen testing background, that report filler on a Thursday at 4:30 p.m. when you've got nothing else. Because, well, you can't go against it. Logjam was a perfect example. Logjam was a great vulnerability, technically unbelievable. The problem was the exploitability part. Very hard to exploit. So we've moved from Logjam, which only had a CVSS score of 4, which was actually a serious vulnerability, to where we're at now with quantum computing. And for that, I'd like to hand it over to my colleague, Dr. Mark Carney.
Thank you very much. So, my friends, Q-Day is coming. Who's heard of Q-Day? Anyone? A couple of people. Q-Day is the day that we have cryptographically relevant quantum computers. That means we have quantum computers big enough and complex enough and stable enough that we can actually attack the cryptography that we use. So when? When is Q-Day? When is Q-Day? It is April 14th, 2030. That's what the Cloud Security Alliance said. Now, for those of you wondering, that's a Sunday, so if you're going to work a weekend, that's probably the one you want to. But this is the kind of estimations that we're getting more and more of. Most people think this is actually a little bit optimistic or pessimistic, depending on your point of view. But there's no doubt, certainly in most of the community, that something is coming when it comes to quantum information and quantum computing. We're just not quite sure what it will be. So what does it really mean? What does a quantum computer becoming cryptographically relevant mean? Let's have a look at some graphs. This is a graph of the classical brute force complexity. So you've got bits going along the bottom. So 1 bits, 50 bits, 200 bits. And then you have a line disappearing up very quickly going vertically. Now this is a logarithmic plot. So what is a 2 to the x becomes nice and straight. And this is noticeably high and to the left. And that's good. Okay? So high to the left and straight. Good. Anything else? No bueno. Okay? So what does a quantum brute force look like? It looks like this. The quantum brute force is a square root brute force attack. It's called Grover's search, for those of you who've heard of it. And it takes a lot of qubits to run. It takes a lot of work to actually code your data into the quantum memory. But if it is successful, what you will find is this change in complexity. So it's bad, right? So what kind of things are vulnerable to this? AES. You no longer have to search the full 128-bit space or 256-bit space. You just have to search half of that. But then it gets a bit more interesting when you look at other crypto systems. So presumably you're all here because you're all RSA and ECC aficionados. Yeah? No? Just me? Okay, fine. This is what classical number factoring looks like. Notice that classical number factoring is a lot easier. This is best case, by the way, in case any mathematicians are wondering. The best case is quite a bit different than just brute forcing, because we kind of have a load of mathematical tricks that allow us to do number factoring. We've looked at factoring numbers a lot. So if I say the secret is 3 and 4, and the answer is 12, it's very easy to verify the answer is 12. But if I say the secret is 12, what did I use to get there? Well, it could be 3, 4, could be 6, 2, could be 1 and 12. Those are all valid. And as the numbers get larger, that space grows out, but in a way that we can kind of keep up with in a way. The danger is the quantum case. Now, for those of you who don't quite know how to read logarithmic plots, that's really flat, okay? In fact, it's n cubed, for those of you who want an exact number. Shor's algorithm. Peter Shor in 1994 released an algorithm in a paper that kind of got everyone to suddenly take quantum computing and quantum information theory much more seriously. And this is why. He showed that the complexity looks like this. And if up and to the left and straight is really good, this is really bad. To give you an idea, you can have quantum-safe RSA keys. But they go from being 4 kilobit, so 512 bytes, to being 9 terabit nearly, which is over a terabyte's worth of key. And with that, yeah, you can probably have a similar level of security that we have today. Just to give you an idea of scale, that's like going from the weight of a paperclip to the weight of 6 blue whales, or 3 fully laden Boeing 747-8s, in case anyone's got a good handle for how much they actually weigh. Have you ever tried to lift one? No? Just me. The reason that we take these threats really seriously is because of other attacks that we've seen. And you might have seen this. This is from 2018. This was a redirection attack that seemed to take place where traffic that was going from Los Angeles to Washington had a little holiday via Shanghai and Hong Kong. If we have people capable, threat actors capable of redirecting traffic, they can just store all of the cryptography. They can store key handshakes, for example, and then they decrypt it later. Hence the name store now, decrypt later. And this is what we're really worried about. To quote Cosmo in the film Sneakers, it's all about the information. So here's what it might look like in terms of a remediation strategy. Who here has data retention policies? If you work in a business, you all have a data retention policy. And it's probably on this graph, okay? You might not be able to read it too clearly, but the UK police are only required to keep data for 2 years, for example. A lot of commercial data is kept for around 4 years. Government records are kept for 7 years. Financial records in a bank, say, are kept for 7 years. Tax records, only 6. You get a year off for free, right? And all of these have to be secured with cryptography. But the cryptography has an overlap period, potentially, with cryptographically relevant quantum computing. So if it takes you many years to implement quantum-safe cryptography, then you're going to have data that is going to be vulnerable to a quantum attack present when quantum computers mature. That's the worst case, okay? Now, if you're dealing with something like government bonds, if you have a government bond tied to a CBDC, central bank digital currency, that cryptography has to now be good for 30 to 50 years. And whatever book you read on the quantum computing trajectory, we're going to see something in that time. We have to prepare for tomorrow, today. Time really is moving on. And whilst you might see headlines, ooh, a step closer in quantum advantage, inching forward in quantum information theory, that's going to keep building and building and building up until the point that we actually have relevancy. So how do we get around this? We need to be cryptographically agile. And we've started this in other areas of tech, Kubernetes and Docker, for example. Gone are the days of an uptime measured in weeks and years, and people being proud of that. It's gone from, I've had a server up for 18 years, aren't I good, to, I never have a Kubernetes cluster alive for longer than 15 minutes. How the good has completely shifted is reliant on the technology that allows us to have agile infrastructure. We need to do the same for cryptography. And to do that, we have to change the way we think about things. As you'll see later, we've even managed to create a standard that is itself agile, a cryptography standard that can be changed really quickly because of how it's stored and how it's put together. We need to enter into several new phases. We need to locate the cryptography we have, and that's really hard. We need to then compare and determine how to fix it, actually go and fix it, and then we need to go round and round, looking at how things change, looking at how cryptographic standards are going to become much more relevant and agile in the future as well. And to tell you more about how this problem works, I'd like you to welcome Dr. Benjamin Rones.
Thank you. Test, is this on? Okay. So where do we start as practitioners with all of this? What are we going to do for our organizations? Well, as Mark just alluded to, crypto agility. If we start with crypto agility, everything else should follow. We'll get to know if we have Q-day risks or general crypto risks, or if your organization is at risk for not meeting its own standards and compliance that are, like I said, organization specific. So if we're going to start with crypto agility, we have to start with locating what you have. You don't know what you have, how are we supposed to start, right? So that just seemed like the obvious first step. And if it's not, it's at least the obligatory one now. Authorities like the US government have recently given White House memoranda and executive orders basically saying know your security posture and explicitly create an inventory of your cryptographic systems to start prepping for Q-Day. So that leads us to the concept of a C-BOM, not to be confused with an A-bomb or the infamous cousin F-bomb. But a C-BOM is a cryptographic bill of materials, and it is exactly what it sounds like. It's an inventory of your algorithms and how they're configured. If you've heard of S-BOM, there is kind of a similar notion here, except S-BOM is for it's a software bill of materials, so that's a little bit more general. C-BOM is going to require more nuanced and detailed analyses, as we'll talk about in a second. If you try to generate a C-BOM for your organization now, I think you're going to ask 3 questions that lead to 3 types of challenges. The first question is, what's the space of possibilities? So what are all the APIs your organization is using for crypto right now? You're probably going to see you have a lot of them. And then in each one of those, there's lots of variability in how an algorithm or configuration of that algorithm is specified. Even one API can have a lot of variability. If you've used the OpenSSL C API, you'll know what I'm talking about. There can be thousands of ways of doing something. The next challenge, once we know the space of possibilities, how do we analyze that space? How do I tell that I have an algorithm or it's being configured? So yes, as previously alluded to, we could do some simple pattern matching and regexes in some cases, but in the limit, you're going to have to trace data sources to data sinks to really know how things are configured, or even to figure out what algorithm you're even talking about. We'll see an example of that in a second. Oh, final question is, once we know the space, once we know or how we're going to analyze that space, how do we codify that space or codify that analysis, or what we call modeling the analysis, into abstractions? So we're talking about, what is a symmetric cipher, or what is an asymmetric encryption algorithm, or elliptic curve. We have these abstractions, and we have to model or take those analyses and put those in those abstractions for each API. So this is 2 challenges. I need an abstraction, which can be kind of challenging in and of itself, but then I have a development challenge for each API in my organization. I then have to effectively develop that modeling or codify that analysis. Let's take a look at the first 2 challenges, the space of variability and data flow complexities. And we're going to look at OpenSSL for C and C++, and asymmetric key generation, because asymmetric key generation is a good example for crypto agility. I need to know where I'm generating keys and if the keys are appropriate size. It's also good for Q-Day concerns because all asymmetric algorithms are going to go out the window once we have a once Q day comes. So we need to know where we're using them and dependent on them. So in this example, if I want to find out where I'm generating a key and what the size is, you can go read the API, or you can just read the English here. It's kind of obvious this set RSA keygen bits. It doesn't actually generate the key, but it at least configures the key. This is something we need to go find, right? And I can see it's RSA from the name, so that's pretty easy. So now I know I have RSA. What's the key size? Well, it's this parameter here. I need to figure out where that came from, and that requires me to use a data trace to go backwards to figure out where that came from. In this case, it came from a parameter, from an outside source, so there could be multiple sources here. And it's also important to realize you may find there's no static source at all. It may come from a file or something, and the trail goes cold in data flow analyses. For a C-BOM, you can't just ignore those. You have to express your known unknowns in that particular case. Let's change the example slightly. Very similar looking example. I just commented out the RSA keygen bit that you could do in this example, but we're not going to. This is perfectly legitimate. So now I want to find out where I'm generating a key, what's the algorithm, what's the size, how do I do that? Well, I see there's a keygen operation, so that should tell me there's key generation, but nothing in that operation tells me what the algorithm is or the size. So again, I need to rely on data tracing to trace this CTX variable, stands for context, back to where it was instantiated, this new ID call above. And again, that's in the API, so I have to know the API, model that API, and realize that that first parameter represents an algorithm. So then I have to trace that. Luckily, it's just right here in the macro that represents RSA. So I can see it's RSA. Great, so we're generating a key for RSA. What's the size? And that's kind of a nuanced point of data flow analysis. Sometimes we're just trying to connect the dots between things. Sometimes we're trying to connect the dots and look for other things that occur on the path. And in this particular case, I'm looking for there's nothing else on the path, no other operation that sets the bits. And that means we have a default key size, and that's based on whatever RSA version or OpenSSL version you're using. So we might call that default or just unknown for our purposes. You could go try to figure out what you statically linked against, but generally that's configurable to whatever you link against. So that could be a problem. Again, in C-BOM, we'd have to note that. So we need an analysis capable of doing, like I said, simple pattern matching all the way up to data flow analysis. And this is where we rely on CodeQL. It's GitHub's tool for source code static analysis. Some key bits here. It supports a wide variety of languages. So that's very important for large organizations. And it's a robust analysis. So yes, we can do simple pattern matching too, but we can do a bit more complicated pattern matching and type checking and things like that, all the way up to interprocedural data flow and control flow analysis. And it also works at scale. So my team at Microsoft, we apply CodeQL to all our products and services before it's released, check if it's free of certain vulnerability classes or meets certain standards and expectations. We also apply it as we see a security incident come in. We extrapolate that security incident into a pattern we can express in CodeQL and go find variants through all our products and services. So we can run at enterprise scales here. And probably more importantly for this audience is it's open source, so you can go try this today yourself. Start playing with CodeQL. Obviously, I can't get into the details of how it works in this talk. So for our purposes, all you need to know is it takes a code base in and effectively turns that code into data, extracts things like expressions and statements, what have you, into what's called a CodeQL database. And then you query that database much like you would query any database with a declarative language that looks very much like SQL, and we call them queries, but it's not SQL. And the results are, well, whatever you were querying for, those patterns, those data flows, what have you. And the format is variable. You can specify serif files, CSVs. You can even get a plugin to VS Code if you want to see it live in your code. So how do we leverage this for C-BOM? Again, well, the queries look very much like SQL. So you have from, where, select type statements. And the C-BOM queries themselves are going to be pretty simple. They're going to be very basic and informative queries. So here's a from, but no where, and then a select. So from asymmetric algorithm, select the algorithm, print its name. So basically, we're selecting the portion of your program that is that algorithm and then telling you what its normalized name is. Very basic, informative query. We're going to have lots of these types of queries. These are just a few, not only for finding algorithms, but also configurations. But what's key here is that abstract class, the asymmetric algorithm, the block mode algorithm, the hash algorithm. Those are abstract classes that are hiding the details of the analysis for you. But the C-BOM queries themselves are basic. They don't need to change. They just refer to these abstractions. I'll get back to that in a moment. But once I have these abstractions, and I can make queries like this that just are informative, what do you have? It's not that difficult to add a threshold on top of that, pull out extra information and say this is an inappropriate algorithm or an inappropriate key size. So for example, using key generation again, I can get asymmetric key generation, asymmetric algorithm. I can pull those out of the program, and I can slap in this size less than 2048. So if I see a key size less than that, I can say that's inappropriate in your system. I could also change it to the size is unknown. I didn't see a statically allocated size. It came from something else. We could alert on that. And you could do this for any sort of vuln, like finding MD5 usage or things like that, bad crypto, or again, your organization-specific crypto standards. And again, it's basically for free at this point. Once you have the abstractions, this part's trivial to apply on top. So the architecture or the artifacts we build for CodeQL here are three things. We have a repository of queries. We just saw some of the example queries for C-BOM, how we could do vulnerability alerting queries. Again, they're very basic looking, using the asymmetric algorithm, one again, for example. But it's referring to these asymmetric algorithms and the like are abstract classes. And you got to think abstract class like your 101 programming class. If you were asked to design a car, you might make a abstract class or interface and then instantiate that for every make and model. Same thing's happening here. The things you can abstract, the algorithms and the operations abstractly, we define here, and they're meant to be predefined. And then you instantiate them for every API you're using. So over here is where you have your OpenSSL version of this, your CAPI, your CNG, your WolfSSL, you name it. And it instantiates these abstractions. So what does an asymmetric algorithm look like in OpenSSL? You instantiate how that looks through CodeQL analyses that are wrapped in these abstract algorithm concepts. But the query up here doesn't change. That's kind of the beauty of this. Once we write the C-BOM queries, they're kind of done. They get more robust in terms of the output as we get more instantiations. And this is where the open source community can come in, and we're hoping that can be the case. We can start by defining the APIs we're concerned about and the level of detail we want there, and then open it up for the open source community to add more and complete the picture. Okay, so we're doing this, again, to recap, for cryptographic agility, and that, of course, gets us Q-Day, and it gets us general cryptographic, or we can find general cryptographic vulnerabilities. And through CodeQL, we get snippets of information, informative, raw data. Like, just here's the algorithm, here's how it's configured. But in terms of a larger C-BOM, it requires a larger context of understanding how that fits in and how all these pieces come together and are formatted. And for that, I'm going to invite Niro up on the stage to discuss that further.
Thank you. Hopefully you can hear me. So I'm excited today because I get to talk about my two favorite things, building Lego pieces and bringing this all together, and application security. So an interesting data point, right? So when we look at a typical enterprise application today that's being built, these applications actually depend on a lot of components to make it happen. In fact, the data today tells us that in a typical enterprise application, over 90% of the software that you're using inside that application comes from open source software. So as we look to scale, the discussion that Ben was talking about, it's great that we have an ability to look at a specific package, but how do we go and understand the complete supply chain that's coming into our application, and then derive from that the complete the crypto bill of materials coming in? And so to discuss how we went on this journey, I'd like to introduce this concept of variant analysis that I think most of you should be familiar with, but apply it to how we use it today actually with CodeQL and GitHub Advanced Security. So to very quickly summarize, I mean, if you're a pen tester or you're working as a security researcher inside your organization, you're quite familiar with this process. Someone comes to you and says, hey, I found a vulnerability. This could be through pen testing or a bug bounty program or through audit logs. And you go through this exercise of diagnosing the problem and then going and fixing the original issue. But what we all understand today is that when we identify these issues, they never ride alone. There may be many other places where this particular type of vulnerability may exist in your code. And this could be because, a junior developer decided to go to Stack Exchange or Stack Overflow and copy and paste the same piece of code in multiple places. Maybe there was a misunderstanding of an API, and so there's misuse of that API happening within the business. And so you want to go through this process of finding it. And today, that process is actually very much browsing through source code or grep as a sidekick. But it's not very scalable. And so this is where CodeQL can help, right? So we can basically codify the problem that we're looking for through the process that Ben described. And then we can go and identify all of the variants of this particular problem across your entire software portfolio, and then go and feed that back to the development teams to go and fix those variants. But once we've described those problems, we can actually then incorporate that into our continual analysis process. So this is not just a one-shot exercise. We can build these queries and incorporate them alongside our existing SAST checks that we have or code analysis checks that we have and continue to improve that suite. And so that concept that we built there is actually known as multi-repository variant analysis. Funnily enough, our marketing team came up with that name, so it's quite a mouthful. But the idea here is that as a researcher, you can fire up VS Code, you can go and look, build a query, and then you can go and run that query across all of the open source packages that exist today that are hosted on github.com. Or you can also look inside some of the private repositories that exist inside your business as well. And so this kind of capability is just kind of showcasing what this looks like here. So as we look to bring these pieces together, our idea then is, can we take those concepts and make it happen? And then the final piece of that is, as we pull that information from, from multi-repository variant analysis, we want to be able to go and build a crypto bill of materials output. And so the great work by Emil and Santander here has enabled us to actually take that output and produce a Cyclone DX output that you can then take and publish and use wherever you require, whether it's for baselining, whether it's for auditing, or so on. And so to just walk through the process that we built out here. So the first thing that we'll be doing is we'll be triggering a C-BOM scan. And the first part of that is going back to our original pictures. We need to understand, what does a dependency graph look like for this application? So we know the code that we're building, but we also need to know the code that's being pulled in as well. Once we have this, we want to analyze the original application and understand what cryptographic algorithms are being used inside it. And then after that, we want to be able to look at the supply chain and start running analysis on the supply chains. And together we can assemble all this data and come back with a single C-BOM for that application. An important step in this process that we'll kind of allude to through the presentation is we've already started caching this information. So if there is a public repository today on GitHub, actually we've started pulling that information and caching it and making that available for all of you to go and access and use. So after this presentation, if you decide you want to go run this analysis, that information is readily available. So let's take a look at a little demonstration. And for this, I have to follow some magic here. So here what we have is a simple Python application to showcase the workflow that we're going through. And here what we're adding is an actions file. And this actions file, the first thing it'll do is it'll actually go through and work out what dependencies you have and what languages. It'll then farm off all the work to do the analysis and then produce a C-BOM. And here we have like a manifest file of the requirements.txt for the Python application. And here you can see we've been able to take that information and build a dependency graph. So now that we've done this, we can go to GitHub and just click on the workflow and say, run a C-BOM analysis. And this will now go through and, as I said before, look at your application and farm off a bunch of activities to go and identify all of the packages and then run analysis to build a C-BOM for each one of those individual components. And so in a second, we should see here a bunch of jobs fan out here, as you can see. So the first set of results we're going to get are basically from packages where we already have cached C-BOM information. And so in about 5 seconds, we'll see this iDNA package come back being completed because we didn't have to do any kind of analysis. We were able to just extract that. And you can see here in the log output from the actions run, we're able to go through and fetch the results. So this is great. So no additional work required. You can pull that. And in a moment here, you can see this is the repository. So this is now open sourced. It has the top 2,000 Python projects based on the OpenSSF criticality standard and the top 2,000 C and C++, and we'll continue to add other languages. But again, this is available for you to pick up and use. If we then go back in here, we should now start to get results where the database was already cached and we cache databases for open source repositories where anyone has done analysis or we see a lot of high use on it. And here we take the database and we'll run those PQC queries that Ben spoke about previously, and we'll do this live as part of the pipeline. And so here you can see the queries that are being run against that. You don't have to read that, but just so you know it's really happening. And you can see those results flowing back. So with that, we have that information, and where we've had to do this manual analysis and it's an open source repository, we will also take that and cache that for future use. And here you can see we create an issue, and this means someone at GitHub will take this and run this in the future. So the next time you analyze that package, that information will be cached and you don't need to do that lookup. And it's all anonymous, so no one knows which packages you're using, it just registers it. So at the end of the result here, we now have the C-BOM that's been built up, and you can see here it's published at the top as a C-BOM results, which is a cyclone.dx file. And then down here, you can see also the content as well. So that basically sets up this process. So this is fully automated, this is live, and this is open sourced. So you have access to that. So now let me jump out of this. Okay, so the other part is, now that you have this information, obviously you all care about C-BOM, you all care about, post-quantum cryptography, but what about your developers who are going to be picking this, seeing these results, and working out what to do? And so here, we can actually start to leverage some of the capabilities inside GitHub today. We have Copilot, for example, and we can apply retrieval augmented generation here. And this is where you can specify documentation within your business on how you want developers or how you want individuals to address PQC-associated issues that are identified in your code. And you can use this kind of chat interface to have a conversation with the developer and let them identify a path that might help them get to a solution that's suitable for moving into the future. And so with that, I'm going to hand back to Daniel, who is the creator of this project, and bring us home. Thank you, Daniel.
Thanks, Niro. So up until now, we've created what might seem like something fairly simple, but this was 8 months of engineering effort and lots of Lego boxes. We now should be able to understand what's in the black box. And as Niro said, what started off initially as us saying, I wonder what open source libraries are post-quantum secure, very quickly turned into well, if we have the cryptographic data, what does it look like? And this behind me is what it looks like. And there were some things that shocked us a little bit. So this is over 4,500 open source dependencies and libraries used currently. We're doing C, C+, and Python. We do have Java planned and Go and other languages, and that's where we're going to be making out to the community. On this graph itself, some of the colors that should concern you. Number one, red is bad, right? Red is not what we want to see. Okay, so that's the stuff that we really need to worry about right now. Red is, for example, MD4. We found over 100 projects using MD4. RFC 6150 said we shouldn't be doing that. Red is SHA-1. A lot of open source libraries are using SHA-1. Now, a lot of the times, it's okay to use insecure old hashing to verify other old hashing. But in the case that we're seeing it, that's not happening. So there's the first problem. The orange is the area that needs the most amount of work. Now, Ben talked about the unknown. Now, the unknown part is really important because we know what we know. We know that there are unknowns, and we know that there are known unknowns. The problem with unknowns is that it's a big indicator of how much effort needs to go into ensuring that the entire supply chain is free from these unknowns. And this was the hardest thing that the team did, was to understand how is cryptography being used in open source libraries. Sometimes we just don't know the key size because it might be in a configuration file. And for me, that's a concern. Because with Q-Day coming on the Sunday, after you've had your Sunday lunch, if you don't understand the library that's nested 9 deep, as Niro said, is using a really insecure RSA key, and you're hoping that that library that you're building the application with is secure, we have a big problem. So what does this look like in reality? this is the one that should shock most people. This is a big graph of understanding the top 4,500 projects. As you can see, we have a bad addiction with RSA. At the moment, over 2,000 projects make use of RSA. We also have SHA-1 in second. Like I said, stuff that we as an industry should know better and should know not to do. We're starting to really understand what's underneath the rug, what's behind the bed. We see MD5 there, we see DSA, we see other algorithms like MD4 and ECB, stuff that we have known for a very long time should not be used. We now have the ability to track where it is. So what we wanted to do with this project is to say to all the open source developers out there who are building stuff in their free time and unfortunately get a bad rap because big enterprises rely on their products that are free and open to build mega million companies. We want to say to these projects, hey, we got your back. And thanks to the help with GitHub, as of today, when you go to these projects, you can now start to see the work that Emil's done with the C-BOM to say, this is where this project is failing. What that means is the community needs to also come to the party. If you can fix the cryptography in that code, pull requests are welcome. But it's quite clear here that we have a hell of a lot of work to do. Now, this project is not a one-fire shot project, right? The other thing we have to do, as Mark alluded to at the start, is rethink where cryptography is used. So one of the things that Mark and I were responsible at Santander was building standards. Now, Ollie talked about it in this keynote today, getting stuff built securely. When we were looking at the initial standard, it was built in a standard like most people did, right? It was a PDF document. It was not friendly to anybody. And we had a moment a year ago, actually, where I decided, ain't nobody got time for that shit, right? So we decided we're going to build the standard as close to the developers as possible. And we used Markdown, and we used it in GitHub. It was open, it was transparent. It also meant that as NIST were going through their post-quantum cryptography ciphers, excuse me, we could rapidly change the standard without having to go through a lengthy process. And this is what we mean about rethinking how we view cryptography. Cryptography is not the bad, hard, unsolvable problem that we've all been told to believe. It is not a bunch of wizards with Birkenstocks, but it should mean that we should be able to understand how we're using it, and more importantly, where it's being used. And up until now, that's always been the killer. Because right now, securing our digital landscape takes all of us. And I know it sounds like a very, very cheesy call to arms, but it really does. Because if Q-Day is indeed happening, we cannot have a lot of the open source libraries being this vulnerable, especially the 84 of them using MD4. So to recap, we understand the risks. We've given a series of tools which are available on the GitHub repo at the moment, and they're available for everybody to use. So we can locate and we can assess. Mark and Emil have built an amazing C-BOM parser that takes Sarah files and allows you to generate a C-BOM, and the C-BOM standard is really, really useful. We can scale the efforts now, where we can now do this for thousands and thousands of repositories, and that's something that the project will continue to do. And we're also understanding crypto agility. So I know it's really bad to give a QR code at, Black Hat, but hey, what the hell, click on stuff, it's fine. All the code repos are there. This is our call for the community here. We really need everybody's help for you to also start scanning repositories of all the libraries and dependencies that you use. As Niro said, we've managed to automate this as much as possible, so you can now tag to get a repository scanned. And more so, that data is all open sourced. So we're being really transparent as how it's being used. Like I said, this is probably one of the biggest research projects I've ever been involved in my career. This is part of the team that built all of this. Like I said, this was a solid 12 months of engineering. So thanks to all the people here who are involved. And more importantly, thanks to all of you who are really hoping that we'll take this project and move forward and help the request library, help Bouncy Castle, help all your favorite dependencies to become a lot more secure. So thank you very much.